As always, I'm your host, Dr. Kelvin. Chemists have long known that substituents can have an impact on relatively aromatic compounds. However, only fairly recently has it been practical for aromatic compounds and patterns of reactivity to be studied through computational methods. Our first guest today is a Hammett Parameter expert and a 3-time Tri-County beer pong champion. From UC Berkeley, please welcome to the classroom, Dr. Aaron Johnson. Dr. Aaron, thank you for stopping by.
Thank you for having me.
I've heard that you and your group have done some pretty neat things regarding the study of aromatic compounds. Tell me a little more about what you guys have done and what you guys have learned.
We studied substituted benzoic acids, and we used the Hammett equation, which states that the base 10 log of K over K naught equals sigma times rho, where K is the dissociation constant of a substituted benzoic acid, K naught is the dissociation constant of regular benzoic acid, sigma is a substituent constant, and rho is a reaction constant. Now, sigma depends on the substituents itself, but not on the reaction, and rho depends on the reaction type itself, but not on the actual substituents. And in order to get our Ks, we used computational chemistry to determine the Gibbs free energy change between the benzoic acids themselves and their conjugate bases. And once we had the change in Gibbs energy, we could relate that to K using the relation delta G equals negative RT ln K. And once we had these, we could use these values to determine our sigma values by setting sigma equal to the log of K over K naught. And then once you have these sigma values, you can relate these to other reactions that are similarly substituted.
Cool. Just to follow up here, how well do your computed values match up or agree with your experimental or expected values?
Our computed values match up pretty well. They're fairly linear when compared to the experimental values. The only thing is that the computed values have a greater slope. The slope's about a factor of 10 greater, and we attribute that to the fact that the experimental values were determined in aqueous solution, and when we calculated ours, obviously in the computer you don't have the same solvent effects that they would have had when they were doing this experimentally.
That's really neat, Aaron. You guys have done a pretty good job. We have a few questions from our studio audience. How are you?
Good, how are you?
Good. What is your name and where are you from, and what is your question?
Madison Gondler from Greensburg, Pennsylvania. Big fan of the show, by the way.
Awesome.
I was just wondering if this Hammett equation applies to all aromatic compounds or just benzoic acids?
Thrilling.
No, this can be applied to other aromatic compounds such as phenols or aromatic amines. So yeah, it's not just dependent upon reactions with benzoic acids.
We got to step aside for a quick commercial break. We'll be right back with more Chem Korner. Our next guest is molecular orbital expert and a world-renowned shoplifter from the University of Chicago, Dr. Samantha Eck. Sarah, welcome to the classroom.
It's actually Sinead.
Whatever. What differences did you notice between the HOMO and LUMO of the molecules you studied?
For the benzene molecule, the HOMO and LUMO were symmetrically distributed and equal in size. For anisole, the HOMO was centered over the para with another lobe covering the ortho positions. For the LUMO of anisole, there were lobes on both the ortho and meta positions. And then nitrobenzene, the HOMO lobes covered the meta position, and the LUMO lobes were smaller and centered over the para and ortho position.
How did these results relate to the activating or deactivating nature of the substituents?
Well, for benzene, the HOMO and LUMO were similar, and that supported the relative unreactivity of the benzene molecule. Whereas for anisole, the small LUMO lobes on the ortho and meta positions support the observed effect of the electron donating groups. And then for nitrobenzene, though the small LUMO lobes centered on the para and ortho positions supports the strongly withdrawing groups directing substituents to the meta positions.
How neat was all of that? That's all the time we have for today. I want to thank our prestigious guests from UC Berkeley, Dr. Aaron Johnson and Dr. Susan Eck from the University of Chicago. Tomorrow, my friend Lenny Pepperbach from the Emmy-nominated hit series Nature Walks will stop by. Until then, remember not to trust atoms, as they make up everything.